Okay, Assalamualaikum and good afternoon. So we continue our lecture on von Karman equation, and now I would like to show you how to use von Karman equation to get the drag force. Okay, why we only focus on drag force? Because we only focus on plate. So because we have only a plate here, so we assume that when a flow like this one, so because the streamline is simultaneously or symmetrically flow on the above and the bottom of plate, so maybe there are no pressure difference, so the lift force maybe not occur. So we just focus on the drag force, because when the flow occur at this area, so the shear stress here will resist the the the, the plate here. Okay. Okay, let's say this is the equation. So determine the boundary layer thickness and drag coefficient in laminar boundary layer that have second order polynomial velocity profile. So and then here, so I hope if this is one example of test and final exam. So at this time, so we ask student to first you need to prove what is the second order polynomial velocity profile. So then after you could prove the second order polynomial velocity profile, then you need to calculate the boundary layer thickness and also the drag coefficient. So this is the basic idea that we learned previously. So the delta is the boundary layer thickness. So the equation is y at u equal to 99% of capital U. So means that we cannot calculate straight away from this equation, because this equation is very simple, and the drag force can be calculated by using this idea. Okay, so I shortcut the process. So you could see my previous note about how to prove the second order polynomial velocity profile. So we know that second order polynomial velocity profile can be written as this one. So and then we have two equation of shear stress. One is von Karman. So this is von Karman. So, and another equation of shear stress is come from Newton. So it is good for you to list down these two equations, because we will use both equation. Okay. So the idea is we calculate, we create an equation from the von Karman, then we calculate, we create equation from Newton, then we equalize these two terms, because when we equalize these two terms, we could eliminate the value of tau. Okay, I hope you could understand this. So saya harap awak dapat faham. Basic idea dia ialah kita mengira dengan von Karman dan kita mengira dengan Newton, kemudian kita akan equalizekan. Okay, kemudian barulah kita boleh meneruskan pengiraan yang lain. Oleh itu, saya harap awak cara yang terbaik yang saya cadangkan di sini, awak tulis velocity profile, and then awak tulislah dua equation shear stress yang telah diberitahu. Okey, so yang ini pun saya ringkaskan oleh kerana saya telah tunjukkan tutorial yang sama di dalam kuliah yang lepas. Oleh itu, untuk mencari nilai theta dengan menggunakan velocity profile ini, saya harap awak dapat mencari, awak dapat masukkan nilai ini di dalam rumus ini, dan akhirnya awak boleh mendapat bahawa nilai theta akan sama dengan 2/15 theta. Okey, kemudian kita menggunakan von Karman equation. Okay, first we are using von Karman equation. So we have von Karman equation, tau is equal to rho u square d theta. So and then it also can be written as rho u square d over dx for theta. So and then theta here can be substituted with the value that we calculated previously here. So now we have terms of this one. So we have tau equal rho u square d dx for 2/15 delta. Okay. So and then the second step, so we calculate using the idea of Newton equation. So we know Newton equation is tau equal mu du dy at y equal to 0. So first what we need to do is, okay, we have our velocity profile u over u. So and then we bring the capital U to the right hand side. So we have u equal to y over delta minus y over delta square. So and then from this equation, we could calculate the value of du dy. So we have du dy 2u over delta minus 2uy over delta square. And then what we do, so because we have condition here, so because we have condition which is y equal to 0, so we need to substitute the value of y here with y equal to 0. So what happened when we substitute the value y equal to 0 here? So we could get that du dy at y equal to 0 is equal to 2u over delta. Okay, means that tau equal mu du dy equal du dy at y equal to 0. So it is equal to mu 2u over delta. Di sini awak kena berhati-hati kerana nilai yang awak masukkan di sini hanyalah nilai du dy sahaja. Sedangkan nilai tau ada nilai mu. Jadi saya harap awak dapat ingat, okay, nilai tau sama dengan mu du dy at y equal to 0. And then kita substitute the value of du dy here dengan apa yang kita dapat. Then we could write tau is equal to mu 2u over delta. Kerana dalam peperiksaan saya nampak ramai pelajar yang betul buat sampai di sini, tetapi apabila dia menulis nilai tau, dia menulis hanya nilai 2u over delta. So itu satu kesilapan mudah yang menyebabkan mungkin awak tidak dapat apa-apa markah. Kerana selalunya kesilapan dalam stage ini, kita kata kita tidak ada memberi markah kesian. Kerana kita anggap ini adalah sesuatu yang awak telah faham daripada fluid mechanics 1. Okay. So now we have two equations. So one equation is from von Karman, equation 1 here. So and then we have equation from Newton law. So we state as equation 2 here. So now we equalize equation 1 and equation 2. So this is equation from von Karman. And this is equation for Newton, from Newton. So here, what we need to do is we need to we bring the delta here to this one. So that's why we have d delta and dx. So and then what we do, we bring the dx here to the right hand side. So we have a dx here. And then because we have d delta here, so means that we need to bring any terms of delta to the right hand side. So we have one delta here. So this delta need to bring to the right hand side. So now we have delta d delta equal to 15 over 2, 1 over rho u square mu 2u dx. So at your right hand side here, it can be any terms. The most important one is, please make sure in your left hand side here, so the only terms that exist on your left hand side is delta and d delta. Okay, boleh faham Kenapa kita akan membuat kameran? Kerana soalan berkehendakkan boundary layer thickness. So boundary layer thickness membawa maksud adalah delta. Oleh itu kita perlu mengeluarkan equation untuk delta. Jadi idea dia apa? Idea dia daripada equation yang kita dapat, di sini, kita kena do something. Kita kena rearrange. So macam mana kita nak rearrange? Awak pastikan di sebelah kiri hanya ada nilai delta dan d delta, dan awak bawa lah semua sekali nilai yang ada ke sebelah kanan. So and then this term can be simplified as 15 mu over rho u times dx. So and then how to get a terms without d delta. So we need to integrate both sides. So we integrate both sides like this one. Okay, so and then with integration of delta d delta, we will get delta square over 2. And then the integration of 15 mu over rho u dx, because we don't have any x, so the x will appear here. So we have 15 mu x over rho u plus c. So c is the constant. So and then we substitute with the boundary condition. So we assume that x equal to 0, delta is also 0, then the value of constant will become 0. So what is the meaning of x equal to 0 and delta equal to 0 here? So you could imagine that we have a flat plate here, and this is our boundary layer. So and then the value at the starting point here, so here the x is equal to 0, then the delta means the boundary layer is not formed yet, so the value of the delta is also 0. Okay. So now after we substitute with the boundary condition, we could get that delta square over 2 is now equal to 15 mu x over rho u. Then now we have an equation without d delta and dx. So maknanya di sini kita telah berjaya menghilangkan sebutan d delta dan juga dx. Saya rasa yang ini awak dah faham. Untuk menghilangkan perkataan dx, dy dan sebagainya, kita akan integrate. Okay, so jadi maknanya setelah kita integrate, kita boleh mendapati nilai d square over 2 equal 15 mu x over rho u. So then from this equation, from this term, we could rearrange the terms until we could get the value of delta here. Kerana apa? Kerana tujuannya adalah untuk mendapatkan sebutan delta. Okay, cuma tricksnya ialah, okay, normally in boundary layer, we will write a lot of equation here in terms of Reynolds number. So means, as you could see here, delta is equal 5.48x over square root Reynolds. So means that at the middle here, in the middle process here, you need to do something to make sure that the Reynolds number could comes out from your equation. So apa triknya ialah, okay, sekiranya kita menyelesaikan masalah ini, kita dapati bahawa di dalam terms ini ada, menjadi 30 mu x over rho u. Sedangkan kita tahu bahawa Reynolds number adalah sama dengan rho u x over mu. So dekat bawah ni kita tak ada x. So jadi apa yang kita buat, kita darablah, kita tambahkan x di sebelah bawah, bermaksud kita kena tambah x, kita darab x di sebelah atas. So that's why we need to multiply this term with x over x. Means when we have x over x, we could have 30x square. So we have 2x here. So we have 30x square times rho ux, and we have mu at the top here. So and mu over rho ux, it is equal to, so mu over rho ux, it is equal to 1 over Reynolds. So now our equation is become 30x square over Reynolds. So because we have a power of 2 here, so we could finally write an equation for delta. So delta here is the boundary layer thickness. So the boundary layer thickness here, so it is equal to 5.48x over square root Reynolds. So this equation, okay, please bear in mind, this equation is only valid for second order polynomial. Why? Because we are using second order polynomial velocity profile. Okay. So if the velocity profile is changed from second order to sinusoidal, so the value of delta here will change. So it means that it is advantage for you to remember the terms of delta here, but please know that this value is only valid for certain velocity profile. Okay, awak kena faham bahawa sekiranya velocity profile berubah, nilai delta juga akan berubah. Tetapi nilai ini 5.48 kita kata fix untuk second order polynomial. So awak buka lah buku teks yang mana, mereka akan menunjukkan nilai yang sama. Okay, next. Okay, we know that the delta is 5.48x over square root real number. So and then, for example, okay, we have a boundary layer here. So kita assume kita ada boundary layer di sini. So macam mana cara nak mengguna delta? So katakan kita ketahui bahawa di sini adalah paksi X dan di sini adalah paksi Y, dan kita katakan at point 1 here the data is X equal 0.4 meter, and then the density is 1000 kg per meter cube, means the fluid here is water. So and then the mu is 0.001 and the velocity of moving fluid is 0.2 meter per second. So how to determine the boundary layer thickness at point number 1 here? So we just fulfill this equation. So first we need to calculate the value of Reynolds number. So Reynolds number can be calculated as rho ux over mu. So we substitute all the value here. So we substitute the value x here with the location here, because we want to calculate the boundary layer thickness at this point. So and then we substitute everything. So we get it is equal to 7.75 times 10 by the power of minus 3 meter. So jadi kalau kita ada 7.75 kuasa 3, so kita ada sekitar 0.000775 meter atau sama dengan 7.75 milimeter. Jadi nilai boundary layer ini kita kata ia adalah realistik. Ia boleh diukur. Maksudnya sekiranya kita ada flat plate dan air mengalir di atas plate tersebut, kita kata boundary layer akan terhasil dan ketebalan boundary layer ini pada kedudukan X sama dengan 0.4 adalah 7.75 meter. So kita boleh ukur sekiranya kita boleh merakamkan fenomena tersebut. Okay, di sini sekali lagi saya harap awak dapat ingat parameter yang mudah, kerana dalam fluid 1 sepatutnya awak telah biasa, iaitu density untuk air adalah 1000 kg per meter padu, dan kita boleh membuat anggapan mudah mu ataupun dynamic viscosity untuk air adalah 0.001 Pascal second. Okey, kemudian saya ingin tunjuk seterusnya berkenaan dengan pengiraan yang boleh kita kira. Okey, jadi seterusnya kita cuba mengira shear stress, kerana ini yang kita bincangkan sebelum ini, bahawa shear stress is quite difficult to be measured. So we need to use equation to calculate or to estimate the value of shear stress. Okay, from our calculation here, we have two equations of shear stress. One is from Newton and another one is from von Karman. Okay, so to calculate shear stress, okay, please remember this one. Okay, to calculate shear stress, please do not use von Karman. Okay, why we cannot use von Karman? Because in von Karman equation, we still have the value of d theta over dx. You may use von Karman actually, but you need to write like tau dx equal rho u square d theta, and then you need to integrate both sides and so on and so forth. Then you could get the same value, because this is actually a very not complicated, but it takes time to solve it. Usually people will use equation from Newton, because equation from Newton it's already in equation form. Yang kalau awak tengok equation Newton, awak dapati bahawa ia telah memberi satu equation yang lengkap. Tau sama dengan mu 2u over delta. Dia tidak ada DD lagi. So jadi maksudnya gunalah nilai shear stress daripada Newton. Okay. Untuk mengira tau. Okay, boleh dapat di sini? Jadi macam mana untuk mengira? So, okay, we know that delta is equal 5.48x over square root Rho. So, and then we substitute the value of delta here into this value. So, if you do the calculation, you could find that tau is equal to 0.365 mu u over x and Rho number. So, this is the equation for shear stress. So, how to calculate the shear stress? So, it's depend on the location of x, because in our equation here, so we have x, and the value of Rho number is also rho ux over mu. So, means it's depend on what location you want to calculate, because the value of shear stress is different between one location to another location. Okay. Yang pengiraan saya tidak tunjuk kerana saya rasa awak dapat imagine macam mana untuk mengira shear stress sekiranya diberi satu titik, diberi X sama dengan 0.2 meter katakan, dan saya harap awak dapat mengira. So, and then we need to calculate the local drag coefficient and drag coefficient, because as I said, the usage of boundary layer is to calculate or to estimate the drag force. Okay. So, di dalam pengiraan ini, parameter yang penting yang awak kena faham ialah, okay, if we have a flat plate like this one, so we have a flat plate here. So, and then the boundary layer occur. So, you must know that this flat plate will have a total length. So, this is the total length of the flat plate. So, the total length of this one, it is equal to capital L, because we will use the idea of capital L here. So, and then, so this flat plate, the drag force here is actually dependent on the width, lebar. Kerana sekiranya flat plate awak panjangnya katakan 1 meter tetapi lebarnya bertambah 2 meter, 3 meter dan sebagainya, nilai resistance ataupun drag force juga akan bertambah. Oleh itu awak kena alert berkenaan dengan soalan yang diberi. Okay, so we go for the local drag coefficient. So, what is the difference between local drag coefficient and drag coefficient? So, local drag coefficient, okay, sama juga untuk molekul di sini. So, we call this molecule velocity is local velocity. So, local here means at specific location. So, local drag coefficient means drag coefficient at specific location. So, for example, we have a point number 1 here. So, the local drag coefficient at point number 1 here. So, it has a specific value. And what is the drag coefficient? So, the drag coefficient is the total drag coefficient for the whole system, for the whole object. So, local drag coefficient membawa maksud drag coefficient pada satu titik yang tertentu, dan drag coefficient membawa maksud drag coefficient untuk keseluruhan sistem. Okay, so macam mana untuk mengira local drag coefficient? It start from the equation of shear stress. So we know from our previous calculation, shear stress is equal to 0.365 mu u over x times square root x. So, and then we could estimate shear stress related with local drag coefficient as this one. Okay, so from where this equation comes from? Okay, please remember that previously, okay, we know that FD is equal CD 1 over 2 tau AU square. So this is actually the simple idea of drag coefficient based on the experimental works. Okay, So how the rho AU square comes out, it is actually the simple method is we could calculate that by using the idea of similarity. So then we compare the equation, what we get from similarity and the experimental works. So we found that the number is not matching, it's not the same. Why? Because there is resistance in the real life, in the real experiment. So we have resistance. So that's why in calculation here we put a CD here, means friction coefficient. Okay, so because this is calculated specifically for drag force, so we call that coefficient is a drag coefficient. Okay, that is the story. You know about the similarity, the Buckingham Pi theorem, and so on and so forth. Okay, so from here, and then we know that force here, it is equal to tau and A. So, and then we could write CD 1 over 2 rho AU square. And then we could cancel the value of A here. So, and then we could write H tau equal to CD 1 over 2 rho U square. Okay, because CD here is for the general one. So we change the CD into tau with C small d 1 over 2 rho U square. So that's why we could say that shear stress also can be simplified as CD 1 over 2 rho U square. So there are no area. Why there are no area? Because we are only calculate shear stress for a very specific location. So means it is a single dot. So means there are no area there. So we eliminate the value of area. So if we have this equation, I think you know what to do. After this, if you have these two equations, okay, so means that we could substitute the value of shear stress here into this term. So, and then we could rearrange the value of CD. So the value of CD will equal to 0.73. And this local drag coefficient is only for second order polynomial, because we are calculated all the terms here by using the second order polynomial velocity profile. So then how to calculate the drag force? Okay, so we go back to the basic idea. So we have a flat plate like this one. So we have width here. So, and then if we have a small area here, how to calculate the force? So we need to calculate we know that force is equal to tau and A. So the tau is shear stress, and A here is the width and also the dx, because dx here is the distance of this small area, and the B here is the width. So that's, so if we write, so the df means a small amount of force only for this area can be calculated as tau B and dx. So, and then how to calculate the total force occur at this area? So we integrate both sides. So integration of d df, so we could get a total force. So that's why I write here as FD, the drag force. And then we have the integration of tau b dx as shown here. And you must remember all the integration must have its limits. So the limit is, because we do the integration on x-axis. So this is an x-axis. So the limit is start from 0 to the end of this plate. So as I mentioned previously, the length of the plate is capital L. So means the limit now is 0 to capital L. So, and then we solve the problem by integrate this term. So we substitute the value of shear stress. So this is the value of shear stress that we get previously. So B dx is the width and the dx. Okay, because we want to do the integration, to dx here, so means we need to expand the value of Reynolds number because Reynolds number contains x. Dalam Reynolds number juga ada x. Oleh itu kita kena pecahkan, kena expandkan, kembangkan Reynolds number kerana kita perlu juga membuat kameran untuk nilai x yang ada di dalam Reynolds number. So we expand the value of Reynolds number here. So we have the rho ux over mu here. So and then you could do because the integration is only for dx. So the idea is you just sum all the value of x. Oleh kerana kameran hanyalah untuk dx, so kita hanya kumpulkan nilai x sahaja untuk kita kamerkan. Kerana nilai yang lain akan menjadi constant, akan tidak berubah. So yang itu saya rasa awak faham pengendalian matematik. Dan seterusnya sekiranya kita menyelesaikan kameran ini, so the limit is 0 to L, then we substitute the value of L, then we get the value of this one. So drag force is equal to 0.73 times capital U square root rho U mu square root L and B. So this is the equation of drag force. Okay, however, because in a boundary layer, we will focus on drag coefficient. So we need to calculate the drag coefficient. So as I said previously, we could assume the value of drag coefficient as CD 1 over 2 rho AU square. So and then CD is equal to 2F over rho AU square. And then A here is equal to L times B. Because if we have a plate here, so the length here is L, capital L, and the width here is B. So and then, so we could substitute the value of FD here with what we have previously here. So we substitute this one into this equation. So we could get the equation for CD is equal like this one. Okay, so and then we could simplify this. I think you already know we have a capital U there, so we have A and so on and so forth. So we could simplify it. Okay, so we replace the value of A. A is the area, so A here is L times B. So you may cancel L and B there, and finally you could have this term. And then the value of rho UL over mu can be simplified as square root Reynolds. Okay, so previously our Reynolds number is rho UX over mu. Okay, then kita kata oleh kerana panjang plate tersebut adalah L, oleh itu kita boleh menukar nilai Reynolds number menjadi rho UL over mu. So jadi di sini kita tukar rho UL mu menjadi Reynolds number. Oleh itu kita boleh simpulkan bahawa for second order polynomial velocity profile, the drag coefficient is 1.46 over square root Reynolds. So this is the value for second order polynomial. And then I hope you could see that the patterns of CD is almost the same, but okay, so we have a CD here 0.73 over square root Reynolds. That is for the local one. And for the total one, so kita tak panggil total lah, kita panggil drag force, drag coefficient sahaja, adalah seperti ini. Okey. Kemudian saya harap pelajar dapat menyelesaikan persoalan di atas dengan menggunakan pelbagai velocity profile. So saya tidak akan tunjuk satu persatu. Saya harap pelajar dapat membuat tutorial untuk perkara ini. Okey, seperti yang saya tunjukkan, sekiranya velocity profile adalah second order polynomial, so kita boleh dapat nilai delta 5.48x Reynolds. C local coefficient 0.73 dan drag coefficient akan menjadi 1.46. So sekiranya kita menggunakan velocity profile yang berbeza, kita akan mendapat nilai yang berbeza. So semua velocity profile ini ada kemungkinan untuk ditanya di dalam peperiksaan. So maknanya saya harap pelajar dapat mencuba di rumah, untuk mendapatkan nilai ini. So jadi kalau awak nak snap gambar boleh, saya beri awak peluang untuk snap yang ini. So ini adalah jawapan untuk 3 profil. Kemudian saya akan untuk 2 profil yang lain, maknanya kuasa 4 dan juga sinusoidal ini yang kita dapat, yang kita ada. So kemudian kita akan melihat satu lagi penyelesaian yang dipanggil Blasius exact solution. What is the difference between Blasius exact solution dan von Karman? So the difference is in von Karman we use idea of U equal capital U at Y equal to delta. But for Blasius exact solution, we will use the idea of at Y equal to delta, U is 99% of capital U. That's why Blasius ni nama orang. That's why Blasius solution is called an exact solution because it use the specific definition of boundary layer thickness. Dia tidak menyelesaikan dengan menggunakan assumption.